Hello and good afternoon friends, welcome to the CEC EduSet live lecture. Dear friends, as you know that we have started with a very new series on stereochemistry, and so far we have conducted two sessions on stereochemistry, taking our series forward. In this series today we are going to talk on the various topics, and the topics would be configuration, CIP rules, RS configuration, and for this discussion we have again with us in our studios Dr. Pankaj Khanna. Dr. Pankaj Khanna is Assistant Professor in Department of Chemistry, Acharya Narendra Dev College, University of Delhi. So dear friends, I would like to welcome our guest Dr. Pankaj Khanna once again, and I believe that this session also is going to be very productive for you, and later on after viewing this lecture you can give your feedback through email. Definitely I would be giving you the email ID, but before that let's carry this lecture forward. So I would like to welcome our guest once again. Dr. Khanna, welcome once again.
Thank you so much. Hello viewers. So today we would be starting from where we left yesterday. We talked about few new concepts about like diastereomers and the relationship of diastereomers with enantiomers, then the racemic mixture, meso compounds. All of these things we have already talked about. Now today's topics, the list seems to be pretty less because the topics are quite lengthy. So we would be talking about what is configuration, as you can see on the screen. Configuration, then how could we define configuration on the basis of the types of configuration. Further we would be deducing the configuration using some rules which are called as CIP rules, and use these rules in determining the absolute configuration or the R or S configuration of the molecule. So going into the topic of configuration, we have already talked about a few things on diastereomers, enantiomers and various stereoisomers which are possible for a given optically active molecule or otherwise chiral molecule. So we are all talking about optical isomerism, and in optical isomerism what is the dependence is the spatial arrangement of atoms. Now I have placed this on the slide. As you can see, I have made the structure of 2-butanol, and because we have learnt about the chiral center, which is the carbon which is having all 4 groups different. In this case we are having the OH, the ethyl group CH2CH3 and methyl group CH3 and hydrogen. So in this case all 4 groups are different, and I have made the one particular isomer of this chiral molecule. This molecule is chiral, it is optically active, and one of the isomers shows the dextrorotatory, the other isomer shows levorotatory optical rotation. So I have drawn, what I have drawn in the slide is one of the isomers possible. Now you can see again on the slide, there is another isomer which we can make by using the mirror image relationship. So what the other isomer is, it is the mirror image of the first one, and they are non-superimposable because of the presence of chiral center. No, chiral center is present, but we should learn that we understood in the previous classes that only chiral center does not make a compound optically active or inactive, but the absence of symmetry or the presence of chirality as a whole in the molecule is responsible for the optical activity. Now obviously when I am talking about 2 enantiomers, one is dextrorotatory, that is it is given by plus butanol, 2-butanol, and the other is levorotatory, that is minus 2-butanol. The question is, which is which? I have 2 isomers written over here, they are mirror image relationship. We can see that, we can see their spatial arrangement, we can see that which groups are coming towards us, which are going away, and what are the characteristics the molecule is having. The 2 isomers I can see here, but how could I identify that the first one is dextrorotatory or the second one is dextrorotatory? So there are a few questions which come into our mind with this, that the correlation between rotation sign and arrangement was needed. When stereochemistry evolved, it evolved to a certain extent. We have done all the experiments done by the scientists. Many more experiments would have been done, which we are not discussing right now, but the problem was that the scientists or the chemists were not able to assign the rotation sign to a given stereochemistry. What do I mean by this? I mean by this that out of these two molecules, which is the dextro one and which is the levo one, they never knew. They knew that there are two possibilities of the structures, but which one is dextro and which one is levo, it was not known. So, moreover, the arrangement cannot be identified experimentally by optical rotation. I cannot deduce, you can see two structures of the enantiomers. I cannot deduce, nobody can deduce whether a given structure would be dextro or the given structure would be levo by looking at the arrangement of atoms. So, it is a big problem. We have to go to a polarimeter experiment, we have to perform an experiment by taking the isomer and we come to know whether it is a dextro one or the levo one. So, if I am having two test tubes with these two isomers, the molecules, then what happens? Then I cannot give which one is dextro or which one is levo by just looking over it, by just knowing it. I have to perform the experiment. Now, the next line suggests that the exact arrangement of groups around the chiral center is what we are talking about. The exact group arrangement of groups means this exact arrangement which I have drawn for two isomers was not being correlated to the dextro or levo till mid of the 20th century. And this arrangement, how we arrange the two stereo how we arrange the groups or atoms in the two stereoisomers is called as absolute configuration. Now, absolute configuration was not known till very recent times, but optical activity, stereoisomerism, enantiomerism, diastereomerism, these things were being studied. Now, what happens? In the next point, we relate to the absolute and relative configuration. If I say that till 1950s or thereabouts, no absolute configuration was available and the isomers were not identified, then how the chemists at that point of time were performing the experiments? How they were relating the specific rotation, say a dextro of a particular isomer to the structure of the molecule. This was done by relative configuration. However, I should put a disclaimer here that besides relative configuration, the problem was still existing. We would come to know what is relative configuration and how they were working. They were defining configuration through the reactions not affecting the chiral carbon atom. So, in this case, we have on the right hand side, you can see on the screen 2-butanol, which is having a chiral center, which we have already made the two isomeric structures in the previous slide. So, it has a specific rotation of plus 13.5 degree, that is one of the isomers was having a specific rotation of 13.5 degree and it was dextro. So, at that point of time it was not available how to do the correlation. What they used to do was they used to correlate the configuration of the dextro wala isomer with another alkene. As you can see in the slide, there is 2-butanol, 2-butene, 1 butene, 3 all. So, this not going on to the nomenclature part, the molecule which I have represented here has a dextro rotatory optical rotation of 33.2 degree. That is, what they tried to do was, or what they used to do between the reactions of optically active molecules, they just correlated the optical rotation of reactant A and reactant B. That means when this alkenol was reduced on hydrogenation, the 2-butanol which was formed was dextro. So, they could correlate that a dextroalkenol gives a dextro alcohol. That is it. We cannot, they were not able to do what was the structure or what was the absolute configuration which I drew in the previous slide for 2 alcohols. That means they were not able to identify the complete stereochemistry of the molecule, but they could correlate between the molecules by doing the reactions which were not affecting the chiral atom. Now, there is no such fixed rule that say alkenol here is dextro and the alcohol is also dextro, but no fixed rule such that compound A would give on a reaction only dextro to dextro or levo to levo. We can have dextro examples which may give a levo molecule after the reaction, but the correlation should be made that there is no reaction on the optically active point which is the chiral center of the molecule. So, no fixed rule such that. Next, we were only this is done, but the problem still persisted. The problem was how to get the absolute configuration of the molecule. Absolute configuration means the geometries, the spatial arrangement I told you at the onset, the 2 isomers I drew there which were optically inactive in the sense that they were mirror images of one another. Those 2 molecules, in those ways we can identify what is the absolute configuration. How did it happen? It came into being by the invention of X-ray diffraction technique. What is X-ray diffraction technique? Like we take the X-ray of any of our body parts, say a leg or a hand, any fractured part. So, when we do the X-ray, what do we see? We see the bones inside us or the solid part through which X-ray does not pass, and it gives the images of those parts. Similarly, this technique is also used in chemistry and solid state physics also, in which you get the similar photograph of the molecule by putting X-ray on them. And what is the difference with other techniques? The difference is that you can get the exact orientation of the molecule, exact arrangement of the atoms on the molecule or the groups on the molecule in 3-dimensional space, thus giving you the overall arrangement of the atoms or group on the chiral center in our case. So, this helped in correlating the examples, and when these examples were correlated, all those things which were relatively correlated, as in the case of alkenol to alcohol, were experimentally identified, and those correlations became successfully absolute configurations for the molecule. So, then we could identify that this molecule, out of the 2 previously defined isomers, the first one, this one is dextro and the second one is levo. Dextro means plus sign, levo means minus sign. So, the one on the left hand side is dextro and on the right hand side is levo. But can you see that I have put intentionally 2 alphabets on the chiral center? On the left molecule S and on the right molecule R. So, what is RS notation, or why do we need RS notation in identifying the chiral centers. For this purpose, you should see that this molecule is here. I have taken one out of the two enantiomers, which is the dextro one. Let us forget what I have told you about X-ray diffraction and remember that we are in say early 20th century and we only know that there is a dextro molecule. We came to 1950s, we came to know dextro is a particular arrangement, say this arrangement is there. So, do not go by the colors of the atoms of the groups, this arrangement is dextro. I have one isomer, I have made only one isomer, this is dextro, but and then I know the geometry, the spatial arrangement, everything, but again go back to those two test tubes. When we go to the two test tubes, how would we identify? Again, we now know the geometry or the stereochemical arrangement of the molecule, but when we see the molecule, unless and until I go and take the polarimeter experiment and identify which is dextro, I cannot write the structure of test tube A molecules on my sheet as one of the two isomers possible, because of the fact that I know dextro, but how to write the structure? The structure I can write when I came to know that dextro is this one by X-ray crystallography, then these are the possible structures I can write. When these are the possible structures, out of the 4 structures, can you identify which is the above molecule I have drawn? You would be surprised to know that all 4 Fischer projection formulae are of the same compound I have drawn in wedge dash, that is plus 2-butanol. When plus 2-butanol is written, it can be written in n number of ways. Now, n number of ways I have written, how would I identify which one is plus 2-butanol or which one is minus 2-butanol, because there is a mirror image relationship. When I can draw 4 same structures of plus 2-butanol, certainly there would be 4 mirror images of these 4 projection formulae and there would be minus 2-butanol. So, it was quite confusing by the fact that you cannot write a particular structure and say I have written one structure and told you this is this. You write it again in a different way and the molecule remains the same. We would come to that what is Walden inversion in a few moments and you would understand what I am talking about. So, coming back to the slide, all those 4 structures needed to be given a nomenclature or a notation, so that I can identify by either ways I do it, by any ways I write it, I would get the same stereoisomer or the same enantiomer in this case out of the 2. So, you can see the next slide says that CIP rules for RS notation. So, what I have been telling about goes into the fact that there was something which was required to write down the structures and to communicate, like we communicate in our language. We know that there is a proper grammar. I am talking in English and I am talking with certain rules. So, we should write those structures in such a manner that anybody who reads it says that this molecule and this molecule and this molecule are same, and say the other 3 X, Y, Z are their enantiomers. So, A, B, C were written in a similar manner and X, Y, Z were enantiomers. So, for this purpose RS notation came to being. What is RS notation? We would come to that RS notation. Before going to RS notation, you can see on the slide that there are certain rules required for identifying RS notation. For that purpose, Cahan, Ingold and Prelog, there were 3 scientists who devised certain rules to identify this RS configuration or absolute configuration. These rules are sometimes called as CIP rules on their names and are also called as sequence rules. So, we would quickly start with those CIP rules. We would start with the CIP rules in the next slide. What we do? CIP rules, we get the priorities to the 4 groups or atoms attached to the chiral center. This is very important, I would be stressing on this again and again. There are 4 groups attached to the chiral center. We give priorities by virtue of these CIP rules to get 1, 2, 3, 4 priorities to the 4 groups or atoms on a chiral center. Number 1 being the highest priority group or atom, and number 4 is the least priority group. Then what we do? We would do certain operations like we did certain things in symmetry elements, similar to those, not exactly those things we would be doing, and from those 4 priorities we would be finding the RS configuration or absolute configuration. So, let us now first start the rules for priority. So, CIP rule number 1 is, CIP rule number 1 says that atom attached to the chiral carbon with higher atomic number gets higher priority. What do we mean by this? So, I have drawn this structure for you. It is a wedge dash formula I have drawn, fluorine and bromine, chlorine and hydrogen. There are 4 atoms and they are all different. So, the chiral center carbon is having all 4 groups different. So, on the basis of the rule written above, the atom attached should be of higher atomic number to get a higher priority. So, what is the order of priority in this case? First of all, we should know the atomic number of the atoms attached to the chiral carbon. Bromine is having the highest atomic number, then chlorine, then fluorine and then hydrogen. So, the 4 groups which are attached, we give the priorities on the basis of their atomic number. So, I am talking about the atoms. By chance I said groups, but you should always remember that you have to look at the atom which is attached to the chiral center. So, in this manner, bromine gets the first priority, chlorine the second, fluorine the third and hydrogen is the least priority group. There is a subset of rule number 1 which is not very much important, but still we should mention it. In case of isotopes, you might say that there is a case in isotopes we have atomic numbers same. So, when atomic number is same, then we should look at the higher atomic mass number. So, in this case the bromine and the chlorine have the similar order of priority, that is 1 and 2 respectively, but I have replaced fluorine with deuterium. So, deuterium gets a higher priority over hydrogen as deuterium has a higher atomic mass. So, the priority order becomes this one. Moving on to the second rule. Second rule, what is it? It says that if we find the same atom attached to the chiral carbon, then we move to the next set of atoms to compare. What do we mean by this? This is very important to understand because usually we get these type of questions in the exams or any other queries which are made to us. So, looking at the previous slide, we had 4 different atoms. Now, we are moving to different groups because there is one ethyl group and there is one methyl group. There is a fluorine which is coming here and a hydrogen atom. So, how do we define the priorities? We would say because fluorine is having the highest atomic number, it gets the priority number 1. Then we go to the other atoms attached. So, you can see in red that I have marked the 2 carbons in red. So, we have the same atom. This is what the rule says. If we have the same atom attached to the chiral carbon, we move to the next set of atoms to compare. So, what do? We have carbon carbon same, we move to the next set of atoms. So, I would see on this red carbon which is the ethyl carbon which is attached to the chiral center, what groups are attached. Again, I would not see what groups are attached. I am only looking at the atoms attached to this red carbon atom. So, I can see here that there is a hydrogen which is attached, as there are CH2, there are 2 hydrogens, and the third one is this black carbon. This black carbon I have written as C. Again, I can compare, I have to compare these set with this one. So, I move on to the next step and I make that this carbon, this methyl carbon has only hydrogen, hydrogen and hydrogen. So, what do? We give the priority on the basis of these. You cancel out one by one. If we cancel out one by one, the hydrogen here gets cancelled out by this hydrogen gets cancelled out by this, and we are left with carbon to be compared with hydrogen. When we compare carbon and hydrogen, remember rule number 1, higher atomic number gets a higher priority. So, methyl is getting the third number for the priority and ethyl is getting the higher number or the second priority in this case. Ethyl wins over methyl. Now, there are certain points to remember in this rule. The points are, when we are comparing the next set of atoms, we should not commit the mistake of adding the atomic numbers. Sometimes what students do, they add the atomic numbers of the next set of atoms and then get a wrong answer. We need not do it. What we have to do, we have to see the atoms attached to the carbon which was same as the other carbon, the 2 red carbons, and just make a set out of those and check one by one. There is another rule which we can say that out of the 2 sets, like in the previous example we are having H, H and C and H, H and H. So, out of the 2 sets, get the one atom of highest priority. The set with the highest priority atom wins over the other set of the atoms, and that group you can say is having a higher priority. Then I can show you this by 2 examples here. In first example, I have taken CHCl2 group. CHCl2 group has, what are the things attached? Hydrogen, chlorine and chlorine, and there is CH2Br group which is attached to the chiral carbon. So, this C is having hydrogen, hydrogen and bromine. So, we have 2 sets of 3 atoms here, HClCl and HHBr. What would be the answer? Can you think over it? What I said, you have to look for the highest atomic number atom out of these 2 sets, which is that bromine. Because bromine has the higher number of atomic number in the 2 sets, B, that is CH2Br, is having the higher priority out of the 2 groups. Sometimes what mistake we do? We mistake by taking into account that, oh, there are 2 chlorides in the first example, first group. So, I should compare, how could I compare 2 chlorides with 1 hydrogen and bromine? This is ambiguous. So, for this purpose I have told you that you just need to see the highest priority atoms, or you may do one thing also, that you can see the highest priority atoms in the 2 sets and compare those things. If you get the same one, move to the next one. So, in this manner you can put off many of the confusions which arise. In this case we are having although 2 chlorides, but 1 bromine, because of the higher atomic number in this B group, has the higher priority. Take another example, CH whole twice, the isopropyl group has H, C and C. This is the H, this C and again this C. This carbon is attached to H and 2 C's. So, I have written HCC is preferred over, on this carbon what are attached? H, H and H, right. So, HCC, by mistake it is HHH, but there is no mistake actually. What I am trying to suggest here is that you should not hurry up into the things like I have hurried just while. What I am trying to suggest that there are HCC which is coming. So, you should not jump onto the conclusion, oh there is O which is coming here. So, this should get the higher priority. You should see that this is not the O which is attached to this carbon. What we are comparing? We are comparing this carbon with this carbon. These two are the carbons. So, this is attached to HCC, but this is attached to H, H and C. The mistake was H, H and it should be C here, not H. So, you should understand that this H, the third H is C here. So, the priority is going to the isopropyl group, this group, because of the fact that there are 2 carbons and 1 hydrogen, and the other one there are 2 hydrogens and 1 carbon. There is no oxygen for comparison. So, easily we can make out that the first one, isopropyl groups, wins over the ethanolic kind of group. Then we move on to rule number 3. If I put an alkenyl group on my chiral carbon, how would I get it? Or an aldehydic group or a carboxylic acid group, because these groups contain double bonds, alkyne contains triple bond. So, we should understand that multiple bonds are also very important to understand. You can look at the slide. The atom which is repeating in the multiple bond is counted one time more as a phantom atom. When we see the structure on the slide, say comparing CH double bond CH2, what does this mean? The ethynyl group is attached to a chiral center. Chiral center has ethynyl group and the other group is ethyl group. So, I have to compare these two groups. When I am comparing the red carbon atoms here, we have, what do we have? We have in the first case, so let us see this we know, the ethyl group H, H and C. So, I have written H, H and C. For the alkenyl group, what I am doing here, I know that this red carbon is attached to the black carbon and it is attached to the hydrogen. So, what I have written hydrogen and the black carbon, but there is no thing I have mentioned in this structure as blue carbon. What is that blue carbon? That blue carbon is hypothetical carbon I have given that this red carbon is attached to, just to make or take into account the fact that this red carbon is attached to the black carbon 2 times. So, I have placed one hypothetical carbon which is called as phantom atom, because I was doing this presentation, so I could make it colored. When you write it in your exam, and you are not having colored pen, what you can do, you can just circle this carbon to make it a hypothetical carbon. Now, what is happening? Because of the fact that this is HC and C and this is H, H and C, we can clearly see that when we cancel out the hydrogens, this is having 2 carbons and this is having only 1 carbon. So, 1 hydrogen and hydrogen get cancelled, this carbon, black carbon get cancelled, and we are left with C hypothetical phantom atom with hydrogen. So, we have this alkenyl group getting higher priority over the ethyl group. One thing you should understand here is that the phantom atom or the hypothetical carbon behaves in a same manner. It has no different properties, because we are just putting a virtual carbon so that we can show that there are 2 bonds the red carbon was making with another carbon. Just to depict that, we are putting another carbon here. Next, we move on to another comparison of this same alkenyl group. Now with this we are having isopropyl group. So make it complicated. So we are making it complicated by the comparison. What is there in the comparison? You go with same carbon. This time around I have put the black carbon as green carbon. It could have been easily a black carbon, that was not a problem. So this remains same, till now it is same. Now we move to the next comparison. Oh, this molecule, the isopropyl group, is having HCC again, because in this case HC and C, this C should have been a hypothetical another colored carbon. So this is a hypothetical carbon which is cancelling out with this is also getting cancelled. So now how do I compare the two priorities? For this matter, let us go back to the rule number 1. When we have similar atoms attached to the chiral center, we move on to the next set of atoms. Now we have the next set of atoms same. We move further to the next set of atoms, and what we get, that this green carbon here in the alkenyl group is attached to the two hydrogens, which are these two hydrogens. These two hydrogens are there, and there is one more carbon which is bonded to this, which is the hypothetical carbon. So this blue carbon comes into picture once again, and we get H, H and C in this set. Now when I compare it with this, any of these are both methyls. So we are not going into the cases where there would be two different groups. We are doing simple things right now. So both are methyls. So I have taken one of the methyls, I have further took the atoms attached, 3 hydrogens. This carbon, green carbon in alkenyl having HH and C, clearly our alkenyl group is a winner again, and alkenyl group gets the higher priority over isopropyl group. Moving on to next, in a similar manner you can do the multiple bonds for alkyne, aldehydes, ketones, carboxylic acid, or maybe if you want to do some difficult examples, you can go on to do benzene and compare with difficult things. So I have taken aldehyde, I am not going into elaborate details like the previous slide, because now we would understand, and you can see, you can understand from the previous ones that CHO, we have aldehydic group, we have the carbon attached to one hydrogen, the oxygen which I have written in black, and because it is a C double bond O group, so I have written O as a hypothetical carbon, giving it in a different color in this manner. If I was having COMe, in this case carbon is attached to double bond O, again one normal oxygen and one hypothetical oxygen, and the other carbon, methyl carbon. So I have written COO. Then there could be the case where I have C double bond OH. So the OH wala O, the C double bond O wala O, and the C double bond O wala hypothetical oxygen. These are 3 oxygens which are attached to this carbon, this black carbon, right. So how can we easily go with the priorities? Yes, the priority order is aldehyde, because it is having one H and 2 oxygens, and the ketone was having we can say it an acetyl group, was having a C and 2 oxygens. So clearly the acetyl group wins over the aldehydic group CHO, and the carboxylic acid was having, the carboxyl group was having 3 oxygens. So it is the highest priority group. So carboxylic acid priority number 1, the acetyl group priority number 2, and aldehyde group priority number 3. Now I have a question for you, you can do it later on. Try to place the ester or CO2Me in the above comparison. when you do it C double bond O Me, you would need, I am giving a hint for you, that you would need to go to the next set of atoms again, because when you go in CO2 Me, you have the same arrangement as CO2H, oxygen of OH, oxygen of OMe, oxygen of C double bond O, oxygen of C double bond O, and hypothetical oxygen of C double bond O and hypothetical oxygen of C double bond here. So, you would be having same things, then you have to move to the oxygen of OH group and oxygen of OMe group, and when you compare OH and OMe, you can get the answer yourself. I have just completed the question, you can do the final thing yourself. We have done the priority order. Now, how to give the RS notation? What I have written here, we have the priority groups for all 4 atoms. We need to go from the least priority group to, we need to place the least priority group to the distance far away from us, and then move from first to the second to the third priority group. What do I mean by this? Let us see with an example. Going back to the bromochlorofluoroethane, priorities order are set. We in the initial slide, the rule number 1, we discussed that bromine is of highest priority, then second number is chlorine, third is fluorine, and fourth is hydrogen. Priority number is set. Then what I have done, what I have to see, I have to see that these 3 groups should be upfront towards me. So, you can see onto my hand, if you can see that I have some of the things, color may be different. These 3 are the blue, red and the yellow, they are the 3 groups or atoms depicting fluorine, chlorine and bromine, any of those. We should not compare it with the structure in the slide, right. So, these 3 are atoms and the white one is hydrogen. So, from your side, when you are looking at the screen, you should have the least priority, the 4th priority hydrogen away from you. The manner in which I have taken it in my hand, these 3 atoms or groups should be towards you and the 4th one is like this. So, why I have drawn the wedge dash formula? The wedge dash formula was like this, these 2 groups coming towards you and these are 2 which are going away from you, from your side. And if I put the hydrogen on the vertical line below, so these 2 are coming towards you and chlorine and hydrogen are going away from you. When I put it like this, these 3 are simply towards you and you can go from say 1, 2 and 3. In which order? The order is not same as in the slide. So, 1, 2, 3. If that 1, 2, 3 movement, like in this case, go into the slide, when we see on the slide, we would see that when we move from 1 to 2 to 3, there is an anti-clockwise movement. The anti-clockwise movement, or we are moving towards the left hand side. When we are moving left hand side, then the configuration is said to be S, and if we move on the have the enantiomer, you draw its enantiomer and move it on the right hand side, you would have the configuration as R. Quickly, there is another way of putting RS configuration when we have decided the priority rules. We have decided priority rules. The other way is drawing Fisher projection formula, giving priorities as we have given and get the RS by simply putting the least priority group, in this case was hydrogen, on the vertical line. Do you remember, vertical line has the groups which are going away from us. So, what we do here, you can see the structure. I have taken 2-butanol, drawn its Fisher projection formula. It is not the final Fisher projection formula. I have drawn it by looking at from this side, in between ethyl and the hydrogen. So, you can draw any Fisher projection formula and use the rules. Rule says that vertical line should have the least priority group. So what I have to do, what I do, there are many ways of doing it. I am telling you the first way. The first way is do Walden inversions. Two Walden inversion. What is a Walden inversion? Walden inversion is that we would exchange these two groups. When we do exchange these two groups, we say that one Walden inversion has happened. One Walden inversion converts the molecule into its enantiomer. When we do another Walden inversion, then we get the enantiomer back, A giving rise to A dash or its mirror image with one Walden inversion, A dash giving rise to A again with another Walden inversion. So you might be thinking this was the basic approach why RS was needed. I was telling you about in the initial part of the lecture that these two structures are same. How do we know that these two structures are same? By virtue of putting RS notation to these molecules. For doing that, I am doing this in this case to make the vertical line group as the least priority group, 4 number. Hydrogen is on my vertical line. To make this, I did 2 Walden inversions and I get the same isomer. Now I have the vertical line least priority group. Now simply what I do, I just see the rotation from 1 to 2 to 3. In this case, it comes out to be clockwise direction. Thus, this is R2 butanol. I hope it is clear. We are having clockwise direction movement and from 1 to 2 to 3 and it is R notation. Moving on to another type of procedure using Fischer projection formula, I again draw the same structure, the configuration in Fischer projection, and this time around what I do, I change this, I take this methyl group here and you can see the arrows, this ethyl group to this side and the hydrogen to the bottom, getting this kind of structure. Again this molecule is the same isomer, not the enantiomer, because you would say that there are 3 changes you have made. Do it yourself, cross check it. These are 2 Walden inversions. Number 1, I do methyl and ethyl, methyl comes here, ethyl comes here, and then do the ethyl and the hydrogen which was placed here. So this amounts to 2 Walden inversions using a trigonal exchange. So I have told you 2 ways of doing it using Fischer projection formula, and these are the 2 easiest way of doing it, and then by doing the 1, 2, 3 I get again this is R. So by using different projection formula I am getting the same R configuration for this levorotatory or L or minus 2 butanol. Coming to a difficult part of the system, which is a 2 chiral center system. For this we take an example of mesotartric acid. Mesotartric acid was the one which was having the plane of symmetry. In the previous lecture we did, it was having a plane of symmetry. So there are 2 chiral carbons, the C2 and the C3 chiral carbons. Now I have to get the C2 and C3 RS configuration. What do? I replace the C3 and the further downside all this into one group and I give it a name as R1. I give it a name as R1. When I do this R1, what is the next step? Next step is giving priorities. When we give the priority, what would be the priorities in this case? You can suggest that this is OH, which is highest atomic number because this is carbon, this is hydrogen, and R1 you have to look at this carbon. R1 is, this carbon is attached to the chiral. So it is again carbon. So carbon, oxygen and hydrogen, OH gets the first priority. second priority. This is an exercise for you. You can do it yourself. You have to compare the carboxylic acid with this group CH-OH, COOH. In this group, the three, because the carbon and the carbon become same, so the atoms attached are hydrogen, carbon and oxygen. When you open up the carboxyl group, you see that oxygen, oxygen and oxygen would compare with H, O and C, and hence carboxylic acid wins this race. You get the second priority on this one. Third priority, this one it gets the third priority because it is attached, the R1 has the carbon attached to the chiral center and it is obviously more in atomic number, greater in atomic number than hydrogen. So, hydrogen gets the least priority in this case. Next, we do the usual thing, we go for the trigonal exchange. This hydrogen will come down, this R1 would go this place and OH would come here. What would we make from this? This is, you have the hydrogen coming on the vertical line, the hydroxyl going to the left side and R1 going to this side. So, I have put the priorities on this, and with the priorities and the hydrogen or the least priority group on the vertical line, I can do the movement from 1 to 2 to 3. And by this you can understand that what is the configuration. In this case it is coming out to be R configuration, for so that it does not become cumbersome here, I have removed C2 from these 3 objects. So, this C2 is this chiral center, that is the first chiral center from the top is having R configuration. Similarly, we can do the second configuration of the second chiral carbon, which is the C3, by putting the above groups as R2. When we put R2 and do the numbering in a similar, I am sorry, the numbering was not there. So, you can do it by yourself, that this way you get the configuration of the C3 carbon as S configuration. Now, you can correlate it with the meso compound. Meso compound, can you look at the screen again one more time? The meso compound is having optical inactivity. It is optically inactive because it is symmetrical and there is a plane of symmetry passing through this. The first carbon was R, first carbon means first chiral carbon C2 is R and C3 is S, and when I draw a plane of symmetry in between, I would note that the R is a mirror image of S. So, when you were having 2 butanol, 2 enantiomers, one was R, the other was S, one chiral center R, the other enantiomer S. In this case, because I am having the mirror image relationship in the molecule, I am having C2 as R and C3 as S. So, this is all about what I have tried to correlate to you about the CIP rules and the RS configuration. Thank you very much.
With this note, thank you, sir. Thank you so very much for giving us a very prolific session once again on stereochemistry. We hope that we would be conducting more session like this on stereochemistry, and very soon we would be back with some more new topics under the series stereochemistry. Dear friends, if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. We would love to solve your queries the next time when Dr. Pankaj Khanna visits our studio. Till then, take care. Goodbye. Thank you, sir. Thank you so very much.